Hello, this is Dr. Keith Miller again. And in this installment of my series of presentations on climate change, we're going to look at weather and climate change. And this is just part one of part two. So this will be divided into two separate presentations. In this first one, we're going to concentrate on the evaporation and condensation of water and energy transfer in the atmosphere. It turns out the unusual properties of water are really fundamental to understand how the atmosphere circulates and to understand weather phenomena. So with regard to water vapor, one of the important things is how much water vapor is in the atmosphere. And the amount of water vapor that the air can hold is called the saturation level. And the saturation level of water vapor increases with temperature. So that means the warmer the air is, the more water it can hold. Okay, this is the potential for holding moisture. So warmer air holds more moisture than colder air. So the colder the air is, the less moisture, the less water vapor it can hold. Something that's probably counterintuitive is that when you add water vapor to the atmosphere, it makes it less dense. So it seems kind of strange that if you're adding something to the atmosphere, it should make it less dense. But the reason is that water vapor, water molecule, which is an oxygen atom and two hydrogens, that molecule is lighter than the dominant gas in the Earth's atmosphere, which is nitrogen. So you're actually adding a light molecule displacing a heavier molecule. So the more water vapor you put into the atmosphere, the lighter it gets. That means that moist air, that is air that's holding more moisture, is less dense than dry air. And so moist air rises and dry air sinks. There are two terms that you need to understand, and that's absolute humidity and relative humidity. Absolute humidity is the amount of water vapor that's actually in the air. So measure how much water vapor is being held in the atmosphere at a particular time and place and temperature. That's the absolute humidity. That's how much water is actually in the air. The relative humidity is the ratio of the actual water vapor content to how much water vapor the air can hold at the same temperature. So talked previously how there's a saturation limit to how much water the air can hold at a particular temperature. And relative humidity is the ratio of how much water vapor is in the air versus how much the air can hold at that particular temperature. And because the air at any given temperature has a limit, a maximum of how much water vapor it can hold, if you keep raising the water vapor content, or alternatively lowering the temperature, you're going to hit a point at which the relative humidity, that is how much water vapor is in the air versus how much the air can hold, is 100%. And when the relative humidity is 100%, that's called the dew point. And at that point, water precipitates out of the atmosphere. Okay? If you have trouble kind of getting a grasp on these concepts, I have a separate short demonstration video dealing with absolute and relative humidity, and that will be on the playlist, and so you can refer to that. Okay, so how is water vapor and global warming connected? Well, we already said that warmer air can hold more moisture than colder air. So as the temperature of the Earth's atmosphere increases, it means that the air can now hold more moisture. And the higher the absolute humidity, that is, the higher the amount of water vapor that's actually in the atmosphere, increases, the amount of rain that can fall increases, right? So the air is warmer, therefore the air can hold more moisture. Therefore, when the temperature hits the dew point and that precipitates out, there's more water in the atmosphere to come out. So this increases the severity of flooding events, simply because the atmosphere is holding more moisture. It also gives the air a greater ability, the warmer air, a greater ability to absorb water, right? So if the maximum amount of water that the air can hold goes up, that means the air can evaporate more water. So this increases the intensity and duration of droughts. This is often a thing that confuses people about global warming and weather, that how can the same changes, same climate change, and in this case towards increased global temperatures, both increase flooding events and increase drought events. And it's because of this fact that this um, case of the temperature of air, the warmer the air is, the more moisture it can hold. So on a global basis, if the atmosphere is warmer and the atmosphere is holding more moisture, it can create more severe rain events. And because the saturation amount is higher, it can absorb more moisture. So in environments where there's a lot of evaporation, that evaporation is going to be increased. So some examples. Okay, so I said increase in severity of flooding events. Just this year, these are two examples. Flooding events are becoming more intense, of a longer duration around the world. As we know, not too long ago, had the flooding in Asheville in North Carolina. Again, around the world, in Nigeria, there have been severe floods. And even more recently, we've had floods in southeastern United States, in Tennessee and Kentucky and North Carolina, again, due to repeated high precipitation events. Conversely, it can increase the intensity and duration of droughts. And again, this is a big global problem, particularly in areas that are already dry areas. The little water that they receive by precipitation is reduced, and again, increasing the duration and intensity of droughts. And the little statement at the bottom, that's from a UN report, says that in the last 30 years, 2.7 million square miles of more humid landscapes have been transitioned into dry lands. So this is a global trend. Connected with increased droughts is fire. And fires, again, are becoming more intense, of greater duration, lasting further into the year than is typical. And again, this is a global phenomenon, not just in the US, but in North America and Asia, and Siberia. These are all trends, global trends of the increasing intensity of fires. Some pictures here from the Los Angeles fires this January, which is also a very untypical time for fires in Southern California. Another important aspect of water is it has what's called a high heat capacity. What that means is the temperature rise is small for a given amount of heat applied. In other words, you have to put a lot of heat into the water to warm it up. Conversely, you have to pull a lot of heat out in order to cool it off. Okay, that's what it means by high heat capacity. In other words, again, you have to put a very high amount of heat into the water to raise its temperature, and you have to pull a lot out in order to lower its temperature. This means that the oceans store a large amount of heat. In fact, the largest percentage of increased temperatures from global warming is going into the oceans. Okay, the majority of the heat that's being generated by human activities is going into the oceans. It's actually increasing atmospheric temperatures, but it's increasing ocean temperatures even more. So the ocean is absorbing a lot of that heat. So here's just a graph starting the 1960s to the present, showing what's called the global ocean heat content. Okay, so this is doing measurements of global ocean temperatures over the whole globe and then tracking that over time. And what you see is this very consistent trend toward increasing heat in the oceans. So the oceans are holding more and more heat. This is another graph showing global sea surface temperatures. So it's just the temperature of surface waters. And each squiggly line is a year. In general, the lines near the bottom of that graph are older. And as time has gone on, the global average sea surface temperatures are rising. And the last couple of years have been particularly anomalous. The yellow line there was the yearly curve for 2023. And the red line there was the beginning of 2024. So I don't have a graph for 2025. But again, these were very anomalous increases in global sea surface temperatures. Another aspect of water vapor is that it has a high latent heat. Latent means hidden. And so when either ice melts or water evaporates, heat is absorbed. Okay, so if you melt ice, you have that ice has to absorb heat in order to change state, right? And when you evaporate water, it does the same thing. Okay, that's called changing state, going from liquid to a gas. When you do that, you have to put heat into it. Okay. Similarly, when it goes from water vapor to liquid water or liquid water to ice, heat is released. Okay, again, that may seem counterintuitive that when you freeze water, you're actually releasing heat into the atmosphere. Or when water is condensing out of the atmosphere, it's actually heating the atmosphere, right? This means that latent heat is the major means by which heat is transferred between the oceans and the atmosphere. Okay, so when water is evaporated from the oceans, that absorbs heat, which cools off the oceans. But then when that water vapor precipitates, cools and then precipitates out as rain, it releases that heat into the atmosphere. And it's this heat transfer from the oceans to the atmosphere that's what powers tropical storms, which we'll look at in the part 2 of this video. So given these things we've already talked about, water vapor has a big impact in how the global atmosphere circulates. So we're going to look at primarily the troposphere. The troposphere is the lowest part of the atmosphere, and it's where all the action is. It's where all the weather occurs. It's a zone of turbulent motion. And within the troposphere, the temperature of the atmosphere decreases upward. So as you go from the Earth's surface to higher in the atmosphere, within the troposphere, the temperature decreases. Now, you can have temperature inversions and other things, but this is the general situation is that as you go up in elevation, the temperature falls. The reason is that the atmosphere is heated from the bottom up. I've talked about this previously in other videos with regard to the greenhouse effect. This is how the greenhouse effect works. Okay, so solar radiation comes through the atmosphere. The atmosphere is transparent. It hits the ground or hits the oceans, hits the water. And that radiation is absorbed by the Earth's surface. And then it re-radiates that radiation, that energy, as heat into the atmosphere. So the atmosphere is heated from the bottom up, not the top down. And the way the heat is moved from the surface, in the case of the oceans, from the surface to the atmosphere is by latent heat, what we just talked about. So let's look at global circulation. So winds are driven by pressure differences in the atmosphere at the same altitude. And remember, I previously talked about if the air is moist, it rises because it's light. And air that is dry is dense and it sinks. Similarly, warm air rises and cold air sinks. So to summarize, warm, moist air rises, cold, dry air sinks. Where the air is rising, we call that a low pressure. When the air is sinking, we call that high pressure. And winds blow from where the pressure is high to where it is low. That's what makes the wind blow. So wind blows from high pressure to low pressure. That is places where the air is cooler and drier to where it is warmer and wetter. And because the Earth's surface is heated unequally, that is, the equatorial belt of the Earth receives more direct solar radiation, and that decreases as you go to the poles, means that the equatorial zone is warmer and wetter. The poles are colder and drier. So as a result, if everything else being equal, and we'll talk what makes it, other factors come into play, but just by that, air would tend to rise at the equator, flow toward the poles, and then sink at the poles, and then flow back to the equator. So you'd have a loop, rising air at the equator, sinking air at the poles, and then the wind would blow from the poles to the equator. So here's a picture just showing the temperature gradient on the Earth's surface. So again, the red band near the equator is where air is rising, and then it's cold at the poles. That's where air is sinking. So if we look at a non-rotating globe, okay, not taking into consideration the fact that the Earth is spinning, in a non-rotating globe, warm air at the equator would rise and flow poleward, cooling and losing moisture as it goes. Cold, dry air at the poles would sink and flow back to the equator at the surface. So it would look like this. Okay, so you have the rising air at the equator, moving northward, sinking, cooling, losing its moisture, falling the poles, and then coming down along the surface back to the equator again. However, the Earth is spinning. The result of this Earth spin is called the Coriolis effect. And the result is that moving air is deflected by the Earth's rotation. So this is a bit hard. There's a lot of videos out there, a lot of really good videos that talk about the Coriolis effect. So if this is new to you or you're confused about it, there are plenty of videos, good videos out there that describe how the Coriolis effect works. But basically, it's a consequence that the surface of the Earth at the equator, that surface relative to an observer outside of the Earth, is moving faster, has a higher velocity than the air at higher latitudes or near the poles. So, for example, the circumference of the Earth is over 24,000 miles, right? The Earth makes one complete rotation in 24 hours, which means that relative to an observer outside, the surface of the Earth is moving at the equator, is moving about 1,000 miles an hour. However, at the poles, if you're just standing right at the poles, all you're doing is making one turn around in 24 hours. In other words, it's effectively stationary, right? That means as wind blows from the south to the north, that the land, surface of the Earth underneath the moving air is moving slower as it moves north. And as it flows south, the surface of the Earth underneath that air is moving faster. And the result is that winds are deflected. It's really an apparent deflection from an observer outside of the Earth. So winds in the northern hemisphere, because of the direction of rotation of the Earth, winds in the northern hemisphere are deflected to the right, and winds in the southern hemisphere are deflected to the left. And the amount of deflection is affected by the velocity of the air and the latitude, how far north and south the air is. So the main thing here is the deflection is greater at the higher latitudes because the change in the velocity of their surface, the rate at which it changes increases as you approach the poles. Because of the fact that the winds are being deflected, so let's say a wind is is trying to move from, in the northern hemisphere, is blowing from the south to the north, it's going to be deflected to the right by the Coriolis effect. So after it moves a certain distance north, it's been deflected so far that it's now flowing west to east. Similarly, in the northern hemisphere, if the wind is blowing from a higher latitude, from north to the south, it's also being deflected to the right, which means eventually, if it moves far enough south, it's going to be moving east to west. And this generates what we call prevailing winds. So you have eastward and westward prevailing winds. So this is a little close. This is still a lot less complicated than reality, but it's a simplification. But showing how that simple pattern that we talked about if the Earth wasn't spinning is now getting broken up into what we call atmospheric circulation cells. And you also have now winds that are not just blowing north and south, but are blowing east to west. So for example, on the equator, you have westerly blowing winds. In the mid-latitudes, where most of the United States is, the winds blow from west to east. So, and we talk about wind direction from where it comes from. So at the equator, we call them the easterlies, equatorial easterlies. And in the mid-latitudes, we call them the subtropical westerlies. So this is all generated by the fact that the Earth spins. And it's true of any planetary body in the universe. Okay, so we look at all the other planets that have any kind of atmosphere, and they behave the same way. If you have a situation where the deflection being caused by Coriolis effect and the pressure difference, which drives wind from where the pressure is high to where the pressure is low, if those two forces are equal, okay, that is the Coriolis effect deflection and the pressure to push winds from high pressure to low pressure are balanced, you get what are called geostrophic winds. And they're commonly called jet streams in popular parlance. So jet stream is a geostrophic wind. The greater the temperature contrast between the cold air and the warm air, the stronger the jet stream. Okay, this is where things get significant. So here's an example. So here we have a wind that's blowing from south to north, from a place where the pressure is higher to the place where the pressure is warmer. Because it's going north in the northern hemisphere, it's being deflected to the right. And it keeps getting deflected. So you see the green arrows are the forces being exerted by the pressure differences, and the red arrows is the effect of the Coriolis effect. And they act in opposite directions. So eventually, the air can essentially stop flowing north at all and just flow to the east in this case. In other words, flow parallel to the pressure gradient. And again, that's called a geostrophic wind. Well, here's one direct consequence of global warming impacting these geostrophic winds. And a very important one is called the polar vortex. So the polar vortex is a jet stream that moves between the warmer air of the mid-latitudes and the very cold air of the poles. Normally, that temperature contrast is very great, very large temperature contrast, which makes the jet stream very strong. As a result, the jet stream, the polar jet stream, which you call the polar vortex, keeps, as you can see on the left diagram, moves basically parallel to latitudes. And it blows in a circle around the North Pole, effectively holding the very cold Arctic air, polar air at the poles, and separating it from the warmer air of the mid-latitudes. Now what happens is, if you warm the air, in particular, you warm the polar air, it's an important point to make here that the poles are warming much faster than the rest of the globe. So the Arctic is warming faster than any other place on the globe. That means that the contrast in temperature between the poles and the mid-latitudes is less. Because that temperature contrast is less, the jet stream is weaker. The polar vortex is weaker, and instead of being this tight circle around the poles, it starts to get really exaggerated wobbles or deflections in it. And that's seen in the diagram on the right side. The consequence of this is that cold Arctic air can now push down into the mid-latitudes. So this produces the kind of a result that's kind of counterintuitive, which is a consequence of global warming is that you get these cold outbreaks in the mid-latitudes. So you can actually have a colder event because the air global average temperatures are higher. So the temperature contrast between the poles and the mid-latitudes are less, actually allows more cold air into periodically, episodically into the mid-latitudes. So just because you have a cold period doesn't disagree with global warming, isn't a counter argument. It's indeed caused by global warming. And again, here is this, we've just had a number of these in recent years. This was in 2014, showing that the temperatures in Alaska were warmer than they were in the Northeast of the US. And again, that's because the polar vortex, the polar jet stream, had really big wobbles in it. And that's what the blue line is with the arrows. That's the jet stream. Furthermore, with weather systems, this is a much smaller scale now. A low pressure system is where the air is, again, warmer or moister than the air around it. That causes the air to rise. As the air rises, it pulls in air from around it. So surface winds blow toward a low pressure system. They then rise, and then they expand in the upper atmosphere. High pressure systems, which are colder or drier air, sink. And as they sink, the air spreads out at the ground surface. So the air diverges at the ground surface, but the air converges in the upper atmosphere. Okay? So you have low pressure, the air is being pulled in, it's being pulled in from the surface toward the low pressure, it rises, and then expands out in the upper atmosphere. And in a high pressure system, that cold air converges in the upper atmosphere and then sinks towards the Earth's surface and then diverges at the surface. So winds then blow from the surface from high pressures to low pressures. Now we can add the Coriolis effect to this. Okay. And this causes not just this rising and sinking, but a rotation as well. So in the northern hemisphere, again, I'm all using northern hemisphere examples. In the southern hemisphere, the situation is completely reversed. So in a high pressure system, the rotation is clockwise. And that's because the ground surface, the air is moving away. In a low pressure, the Coriolis effect will cause a counterclockwise rotation. So winds circulate counterclockwise around low pressure systems and clockwise around high pressure systems. So here's an illustration. This is low pressure. The air wants to blow toward that low pressure from high to low, but it's being deflected to the right. So as the wind approaches that low pressure, it kind of misses it to the right and then it's pulled in. And so it ends up rotating around that low pressure counterclockwise. And here is a composite satellite image of the Earth. And if you see in the upper part, upper left-hand corner, there's a large low pressure system. And you can see that that spiral is counterclockwise. If you go into the southern hemisphere at the bottom of that image, that's another low pressure system, but there the rotation is clockwise. So again, rotations in the southern hemisphere are opposite of those in the north. So this ends this part one of this video. Again, there'll be a part two, which will continue our discussion of the impact of global warming on weather events.